Hey there, young scientists! Get ready to be pulled into the amazing world of gravity and static electricity at this physics museum adventure. I'm here in a studio, but this isn't an ordinary studio. This is a flying studio. Next to me, in the floor, is a hole. Let's first have a look at the reason why I'll fall down and don't stay floating in the air when I jump into this hole. Hey you! Wanna jump with me? Have you ever wondered why you always land back on the ground, no matter how high you jump? Whether you jump on a trampoline, on a couch, or on the floor, you always end up back on the ground. How does that actually work? Look, I've got two golf balls, a yellow one and a green one. The yellow one weighs 46 grams, the green one just 10. Now I drop them both, at the same height and exactly the same time. What will happen? Let's see. Hey, did you see that? They hit the ground at the same time. The heavy yellow ball did not fall faster than the way lighter green one. Do you know why that happens? This is due to gravity on Earth. Everything on Earth falls at the same rate, regardless of weight. Look, I've got two sheets of paper, a yellow one and a green one. They both weigh 5 grams. Now I crumple up the yellow paper into a round web. Now I drop them both, again from the same height at the same time. What do you think is going to happen? Hey, did you see that? The web fell faster than the sheet of paper. Why is that? Well, everything that falls encounters air, and an A4 sheet of paper encounters much more air along the way than one that has been crumpled into a web. The air slows the fall of large light objects, and that's why the web is down sooner. If I were to stand in a room where there was no air, the web and the sheet of paper would fall just as quickly. But why? How can you calculate that? Well, you can with the universal law of gravitation, invented by Isaac Newton. He said that the force of gravity is equal to the weight of object 1 times the weight of object 2 divided by the square distance between the two. But if you were to calculate this, the force of gravity between me and this book would be so big that the book would slide towards me, like this. That's when Newton came up with Big G. Big G is very small. If we place Big G here, the force between me and the book is smaller, just right for gravity. To calculate this, we need fixed numbers for our variables. Let's say I weigh 45 kilos and the book weighs 1 kilo. The book is 2 meters away from me. G is, as always, 6.673 times 10 to the negative 11th power Newton meter squared per kilogram squared. First, we square the distance. 2 squared is 4. Then we cancel out the meter squared with the meter squared and the kilogram squared with the 2 kilos. Let's put aside the times 10 to the negative 11th power and calculate the formula. 6.673 newtons times 45 times 1 divided by 4 is 22,544.79723. Now the decimal point isn't where it needs to be, so let's roll it to the place where there's only one digit before the point. Then we add the times 10 to the negative 11th power again and we add the number of spaces we move the decimal point to the exponent of 10 to the negative 11th power. Here we move the point 4 spaces, so we add 4 to negative 11. Negative 11 plus 4 is negative 7, so the final answer is 2.254479723 times 10 to the negative 7th power Newton. From falling golf balls and paper to big G and 10 to the negative 11th power Newton, these are the basics of gravity. I talked about jumping, falling, air, Newton's universal law of gravity, and the calculation of that formula. I hope you learned something. Bye! Hey, how did I end up in another studio? Maybe I was attracted by some kind of giant balloon. Anyway, we are now going to watch a video of a party where lots of strange things happen. Imagine you're at a party. There are balloons. There's confetti. There are cute butterfly ornaments. You blow bubbles. You drink through clear straws, so you can see the juice coming into your mouth. And, best of all, there's cake.
But there's something strange going on at this party.
Some balloons move towards you. Two other balloons repel each other. And the confetti jumps onto the balloon. The butterfly ornaments turn towards the balloon. The bubbles are moved by a straw. And you can move the straws without touching them. On top of all this, when you want to take a bite of that delicious piece of cake, hey, the sprinkles jump to my spoon. As you might already think, I haven't shown you everything. Before filming the balloons coming towards me and repelling each other, I rub the balloons on a wooden sheepskin. Before filming the jumping confetti, I rub the balloon. The same goes for the butterflies. I rub the balloon before filming them coming towards it. As for the moving bubbles, I first rub the straw with a piece of silk cloth. And before I filmed the moving straw, I also rub the straw. And to get all those colorful sprinkles to pop onto my spoon, I rub the spoon first. What do all these examples have in common? Exactly, the rubbing. Rubbing these objects creates static electricity. Let's take a closer look at two of these, the jumping confetti and the repelling balloons. I will also include the other experiments, but I won't explain them as extensively as the confetti and the repelling balloons. First, those jumping pieces of confetti. If I rub this balloon on some wool, the balloon becomes negatively charged because the electrons in the wool jump onto the balloon. The pieces of confetti are slightly positive. Positive and negative charges attract each other, just like the north and south poles of magnets do. If I hold the balloon above the confetti will be attracted to the balloon. If I hold a negatively charged spoon close to the positively charged sprinkles, the same will happen. The same thing happened when the balloon came towards me. The moving bubbles? Again, the negative straw and the positive bubble attracted each other. The moving straw is also based on this. By the way, I put a needle through this plastic cylinder so that the straw can balance on the tip of the needle and spin freely. This is a fun and simple game that you can play with just a straw, a needle, and an object through which you can push the needle. Remember the butterflies that were attracted by the balloon? You can play a funny game with this. Look, I drew a flower on this balloon. And now, when I charge the balloon, the butterflies are attracted to the flower. Oh, they smell the delicious nectar. Do you want to play this at home yourself? Check out the description box below the video. I drew a template so you can make such butterflies yourself. Cut the body from standard paper and the wings from a light type of paper, such as kite paper or tissue paper. I use tissue paper. Cut out the shapes first and use them on the paper you want to use for your butterfly. Make sure to fold the paper in half for the wings and place the fold line of the template on the fold of the paper, like this. This way you will have one set of wings attached together, which you can glue to the body, like this. To make your butterflies fly, attach a thin fishing line to them, making a loop for hanging. Create two cute antennae by leaving a piece at both ends of the loop. Now the two repelling balloons. Why wouldn't they touch each other? Well, that's because by rubbing, both balloons got negative. Negative and negative repel each other. The same happens with positive and positive. They also repel each other. Again, this is a bit like two magnets with the North Pole parts facing each other. They will also repel each other. The formula for this is very similar to the universal law of gravitation, but this is Coulomb's law. He stated that the electrostatic force is equal to the charge in coulombs of object 1 times the charge of object 2 divided by the square distance between the two. Looks familiar, right? And again, the force between, for example, these balloons is still too strong. So Coulomb came up with lowercase k. Lowercase k is a very small number. If we place k here, the force between these balloons is smaller. Just right for static electricity. To calculate this, we need fixed numbers for our variables. Let's say I charge both balloons 3 times 10 to the negative 8th power coulombs and they are half a meter away from each other. K is, as always, 9 times 10 to the 9th power Newton meter squares per coulomb squares. First, we square the distance. Half a meter squared is 0.25 meters. Then we cancel out the meter squared with the meter squared and the coulomb squared with the 2 coulombs. Let's put aside all the exponents, times 10 to the 9th power and the 2 times 10 to the negative 8th powers, and calculate the formula. 9 newtons times 3 divided by 0.25 equals 324. Now the decimal point isn't where it needs to be, so let's kick it to the place where there is only one digit before the point. Then we add all the exponents up. 9 plus negative 8 plus negative 8, or 9 minus 8 minus 8, and that's negative 7. Now we add the number of spaces we move the decimal point to the exponent of 10 to the negative 7. Here we move the point 2 spaces, so we add 2 to negative 7. Negative 7 plus 2 equals negative 5, so the final answer is 3.24 times 10 to the negative 5th newtons. Remember we started at a party? Well, a party isn't fun without presents, is it? That's why I have a gift for you. It's this video with new knowledge about static electricity and a fun craft to actively work with your knowledge. As I said before, check out the description box below the video to download the template I drew, so you can make your own butterfly craft. To close this present to you, I would say blow up some balloons, take some wool, silk or another type of fabric, or dry your hair, and have fun with static electricity. I will certainly have fun with static electricity. Thanks for the new knowledge and the template, and you gave a very good explanation of all the weird things happening at that party. As you already saw, the universal law of gravitation looks a lot like Coulomb's law. I'll now compare them, so you can see what is the same and what is different. What we see is that both laws describe forces between objects at a distance from each other, and they both use a constant to make the force smaller. Also, they both square the distance between the objects. Newton's law of gravity concerns the mass of the object and the attraction between different masses. Gravity is always attractive and acts on all objects with mass. Coulomb's law concerns the charge of the object and the attractive or repulsive force between those charges. Electrostatic forces are either attractive or repulsive and only act on charged objects. Newton's law involves the gravitational constant big G, while Coulomb's law involves the constant K. Gravity is a weaker force than the electrostatic force. The electrostatic force, which is described by Coulomb's law, is about 10 to the 36th times stronger than gravity. The charge of an object can be much greater than its mass, leading to a stronger electrostatic force compared to gravitational force. And the force of static electricity depends on the medium, the stuff between the objects. When the medium is air or a vacuum, K is what I said before, 9 times 10 to the 9th power. When a medium is something else, like water, K is also different, so the force also is. Newton's law of gravity and Coulomb's law agree that the force between the objects quadruples when the distance between the objects halves. This is also called, difficult word alert, an inverse quadratic relationship. Now we've come at the end of this video. By our exploration of gravity and static electricity, we discovered what they are and we compared them. Gravity pulls objects towards other objects because of their mass, while static electricity pulls and pushes between objects by their charge. Both are important forces in our world and they help us understand how physics works. See you next time!